Thank you for coming. So, my name is Andrey. I came from Olomouc, where I worked in the group of Rising Tube. So, Olomouc, here it is on the map, it's in the Czech Republic. If we zoom in closer, you can position within the relevant part of Europe. Okay, so in Olomouc, there is indeed the Rising Tube group. Here I took a screenshot of one of his talks from the COVID era, 20 years ago, so this is a bit outdated. The group really has very many people who do very many different things. There's a sub-branch that does optomechanics, where some of these people are on this slide. Okay, this slide is already quite outdated. This Louis, who previously worked here, has already left us as well. So people come, we can go. We have some positions, so if you become interested, please talk to me. Right, so before I start, let me give you a brief overview of the things that I will talk about. So I will try to convince you that in a system which is formed of a levitated nanoparticle inside an optical cavity, by an appropriate driving and readout, we can generate remote squeezing, and what's more important, we can sort of generate it in a more optimal way that we previously thought, and also detect it in a more optimal way. Well, in order to be able to convince you, I will try to give an introduction into the field of optomechanics, what that is, what's so special about levitated optomechanics, and how to generate and detect unpositive relations there. Yeah, I've already quite a bit of you there. First let me start from a brief introduction to the history of the optomechanics. Well, it essentially started in late 1960s, when these two gentlemen realized that it's possible, by shining appropriate electromagnetic field onto different objects, mechanical objects, they realized that it's possible, by doing so, to control the properties of the mechanical motion. So Andrey Rakhubovsky has received a Nobel Prize for that quite recently, and Vladimir Palacký was very instrumental in the development of the gravitational wave then. And both such systems, such as a trapped nanoparticle, a dielectric nanoparticle, and the huge masses of the gravity wave antennas, are both essentially optomechanical systems, because in both of them there is some coupling of electromagnetic fields to the mechanical motion through radiation pressure. And since then, there was quite a number of new platforms emerging in the field, which range indeed from the very macroscopic mirrors of the gravity wave antennas, which have the masses of tens of kilograms, to micro oscillators, to mechanical micro oscillators, nano oscillators, and eventually to trapping single atoms in cavities, which in some sense are also optomechanical systems. So studying such systems is interesting for a number of reasons, in particular mechanical oscillations, naturally coupled to pretty much everything, such as different fields, so you can use them to perform sensing of whatever you want, such as forces, masses, accelerations, and so on. You can do that potentially at the quantum level. Since these mechanical oscillators, but most of these oscillators are quite macroscopic, which means that they're very heavy, you can study some fundamental science, so basically macroscopic quantum mechanics. You can study how do really big objects behave at close to the quantum level. You can study what's called quantum to classical transition, trying to figure out where is the line beyond which the objects start behaving quantumly, or if you go in the opposite direction, when the quantum objects start behaving classically. Also, I put here these two items separately. This quantum measurement theory and spin-spline generation were, I would say, the two most practical outcomes of the development of the gravitational wave detectors. And therefore, it's quite difficult to draw a separation by separating line between the fundamental physics studies and the applications of mechanics. So I would say that optomechanical systems are rather simple. In some sense, they're rather simple, but they have very rich physics, which has potentially lots of interesting outputs. what's good for us theorists, and well, I pretend to be a theorist as well, is that most of the systems, they can really be described by a model of a Greek cavity with a movable mirror. So the very typical toy model really looks like this. We have an optical cavity with the field circulating inside, and it has a movable mirror. So basically, when there is light inside the cavity, the light pushes the mirror. It makes it move. Also, there might be some forces which also make the mirror move, but importantly, there is this radiation pressure force which really pushes the mirror. When the mirror moves, the frequency of this cavity changes, and this causes some effects on the light in response. So, in principle, this is still quite a complicated system because the cavity can have multiple optical modes. The mechanical displacement field can also be multi-mode. If we just look at the membrane, let's say if this was a membrane, or if it is a mirror, it has different modes of the oscillation of the surface, each of which can impact the state of the field. But for simplicity, we really assume just a single mode cavity, which couples to a single mode mechanical oscillator. So we somehow do this proper quantization, and we throw away all the irrelevant modes, which happens to describe the actual experiments with a very good level of precision. Okay? Right, so if we decide to write the Hamiltonian of such a system, we essentially just have two oscillators. Like the cavity mode is one oscillator, and the mechanical mode is another oscillator, and the Hamiltonian is really very simple. So the cavity mode is just a harmonic oscillator whose frequency is a function of the position of the displacement of the mechanical mode. So if we expand this function into series, and we're quite happy with just the expansion up to the linear term, we're going to get this optomechanical radiation pressure coupling interaction, where from the point of view of the mechanical oscillator, this term is just a force. This is the radiation pressure force which couples to the mechanical position. Okay? Unfortunately, the prefactor in front of this force, which is the coupling rate, essentially is very small because this is the derivative of frequency with respect to the position. Essentially, it has the meaning of the shift of the cavity frequency per single phonon of the mechanical oscillations, which you can guess is a very tiny quantity. So, fortunately, it's very difficult to see these effects truly at the quantum level. So, in order to be able to see them with mechanical oscillations at the quantum level, this interaction is normally enhanced by a strong classical driving. And the strong classical driving essentially creates strong coherent components of both optical oscillations and mechanical oscillations, around which we can linearize this interaction. And therefore, we exchange the nonlinearity of the coupling for the strength of the resulting coupling, which can be, let's say, non-negligible. Okay, so let me briefly summarize what that means. So, when we have done this linearization, then we have sort of three main participants of the optomechanical interaction. The first of which is the strong classical pump, or the strong coherent drive of the cavity, which normally we assume to be slightly detuned from the cavity resonance, right? On the resonance of the cavity, there lives the quantum, fluctuations of the optical mode, and we also have the quantum fluctuations of the mechanical mode. Let me remind you that this is inside this displaced picture where we have eliminated the strong classical displacements generated by the strong classical drive. Okay, so we have essentially two quantum oscillators now, this mechanical B and optical A. They are linearly coupled by the coupling, which depends on the type of the drive that we choose. Okay, right, so this is still, we can say that this is still, let's say, sufficiently complicated Hamiltonian. We want to make it simpler, so we go to the frame which rotates at the which performs rotations defined by the free Hamiltonian. So these two modes, right, and in this rotating frame we have this Hamiltonian, which, well, it's quite typical treatment have this Hamiltonian where we can search for the terms which are fast or slow, and then depending on the tuning of the drive, right, if we choose one of them, we can keep only parts of the terms from this Hamiltonian, right? So if we drive on the lower, if we drive our cavity on the lower mechanical sideband, right, we can see that some of the terms in the Hamiltonian are now rapidly oscillating, which we will ignore in the protected frame, and we will keep other terms. So if we drive on the lower mechanical sideband, we are going to have an interaction like this, which is the excitation hopping type interaction. If we drive at the upper mechanical sideband, now this photon hopping as photon or excitation hopping interaction is now off resonant, but this pair annihilation interaction is now present. Okay, like if we look at it carefully, then we can summarize it like this, right? If we drive at the different frequencies, so basically if our drive is tuned to the lower sideband of the cavity resonance, which is here, right, that what can happen is that we can take a photon of pump, we can combine it with a phonon of the mechanical oscillations, and these two excitations can be annihilated to create a single photon of the cavity. So this is basically this term, right? We create a photon of the cavity by annihilating a mechanical phonon. And somewhere outside of the brackets, there is the classical drive, which sets the strength of this interaction. And there is an opposite process where we can annihilate a photon of the cavity and create a phonon of the mechanical oscillation, right? And well, let's say for the theorists, this Hamiltonian is very known as a parametric conversion Hamiltonian or parametric converter, or just a beam splitter between the two modes described by the operators A and B, right? In practice, this interaction can be used in order to either swap the states between the cavity mode and the mechanical mode, or it can be used to cool down the mechanical oscillator, which is essentially the same because we're trying to substitute the thermal state of the mechanics by the cool or ultimately vacuum state of the cavity. Okay, good. And then for the opposite situation, when we drive at the sum frequency, so our pump frequency is now the sum of the cavity and the mechanical mode. If we do so, then when we take, well, one photon of the pump can now be split into a pair of the resonant cavity photon and the mechanical photon. And this is this term in the Hamiltonian, and there is a function conjugate which takes two excitations of our quantum modes, annihilates them, and in exchange provides one photon at the pump frequency. And this Hamiltonian is known as the parametric amplifier, or equivalently the two-mode squeezing. And in practice, it is known to generate entanglement between the participating modes. So in this talk, I will use this type of interaction, or will assume that I can use this type of interaction in order to create entanglement between optics and mechanics. Okay, let me remind you that when I was deriving these Hamiltonians, I threw away other terms which are off-resonant. So the requirement for this is that the mechanical frequency is significantly larger than the cavity line. So basically, this makes one of these processes resonant, and the opposite one strongly off-resonant. So this is called result sideband condition, and for quite a number of optomechanical systems, it actually works.
But in principle, you can solve exactly this Hamiltonian without these approximations, yes? I mean, to evolve Gaussian states with this Hamiltonian.
I mean, this one.
This upper one, yeah.
Yeah.
Yes. So it's not strictly necessary to make this approximation, just to simplify the picture.
Absolutely.
And then you don't have a nice picture of beam splitter or squeeze.
Well, you do have, but it's contaminated by the second process. And sometimes it is actually helpful. But I will get to exactly that point, actually. Okay, right. Why we do this is to really see the sort of dominant physical process, which sort of plays the main role if we manage to get into the proper region of the parameters. Okay, so, well, this was supposed to convince you that in optomechanics, what people have mastered to do is that they now have pretty rich Gaussian toolbox, which the people have also mastered in quantum optics. So basically, two more squeeze and beam splitters, and from that we can make combinations of instructions. Right. Well, this talk is about non-particle states of the levitated optomechanics, so I will spend some few minutes on essentially promoting levitated optomechanics. Because the results of this talk can be equivalently well applied to other optomechanical systems. Okay, so what's so special about levitated nanoparticles? Well, if you have a dielectric trapped inside, or if you have a dielectric in an electromagnetic field, well then it will likely become polarized, and if the trapping field, well, if the field around the dielectric is inhomogeneous, then this particle will feel the force, which will drag it towards the intensity. If the intensity field is inhomogeneous, so basically there are places where the field is stronger, then the particle will be dragged towards the point where the field is stronger. Mathematically, it looks like the effective potential for the mechanical motion is proportional to the intensity of the trapping field. And so if we trap the particle in a Gaussian intensity profile, then close to the center or close to the focus of this Gaussian beam, we will have an effective potential of the mechanical motion, which is very closely quadratic. So our nanoparticle becomes a mechanical oscillator with the frequency which is set by how tightly we can focus the laser beam. Okay, right. If we go further and if we somehow manage to engineer more complicated, like more complex intensity profiles, then we can go beyond this quadratic potential and we can think of generating nonlinear potentials. For instance, such as a cubic potential. This has been done at the classical level by the people from Brno. And the people in Vienna now want really hard to do this at the quantum level. Right. We can think of, let's say, further possibilities. So if somehow we manage to trap the particle at the intensity minimum, then we will have the inverted quadratic potential of motion. And what's even more atypical for the, let's say, if your optomechanical system is just a fabric probabilities where one of the mirrors is movable, this mirror likely has a frequency which you cannot really tune very free. But if you have a levitated nanoparticle, you can switch the tweezer off at all, which means that there is no more any trapping intensity, which means that there is no mechanical potential whatsoever. So the particle is really just a freely falling object, which is the possibility that in fact is just unthinkable with what's called clumped oscillators, so with material oscillators. So this is why the levitated nanoparticles, they attract lots of attention when it comes to, let's say, control of the mechanical motion. Right. So the takeaway point here is what I did not say, unfortunately, for that is that on top of that, for the levitated nanoparticles, we have all the previous outcomes of the standard Gaussian optomechanics, so to say, which means that the levitated systems offer you all the advantages of the optomechanics plus the different mechanical potentials, plus the possibility to engineer mechanical potentials. Okay, but now we're going to the non-classical correlation. So, I guess you've seen before, if we tune the optomechanical cavity properly, we can realize the two-mode squeeze interaction. And two-mode squeeze interaction, described by well, it is known to be capable of creating entanglement in the participating modes. Now, the issue is that the two-mode squeeze interaction takes place between really the mechanical mode, the mode of the mechanical oscillations, and the intracavity optical mode. Unfortunately, we do not have the access to this intracavity optical mode, so we cannot really look inside the cavity. We have to somehow manipulate with the light which leaks from the cavity. And while this is a single mode, let's say by our convention, we have a single mechanical mode and a single optical mode inside the cavity. Unfortunately, the leaking field is a propagating field, so it is fundamentally altered. Therefore, if we want to make statements about the entanglement generated by the intracavity optomechanical interaction, we have to do so based on our measurements of the output field. And since this is a multimode field, we have to filter it cleverly to basically look at exactly that thing which tells us about the entanglement. Okay, and after we have chosen the proper filtering for this multimode field, then we have to think, how do we extract information about the entanglement from that? Okay, that's more about it later. Excuse me. To give you a somewhat pedagogical example, let's consider very briefly the problem of readout of the quantum state of a cavity field. Let's assume that at the time t=0, I have here inside of my cavity, and this is now just a bare cavity without any optomechanics whatsoever. It's just a single cavity. But let's assume that I have here an interest in quantum state, and I want to learn it. And I can only learn it by measuring the field that leaks from the cavity, because I cannot really open the cavity and look inside. I have to measure what leaks outside. So how do I do that? Well, I can write the Landesmann equation for the intercavity field, and it has a very trivial solution, just the exponential decay plus the noise. And I can write the input-output relations for essentially the boundary condition on this cavity mirror, which will give me the field that leaks from the cavity. And I can see that in the expression for the field which leaks, I have the part which is proportional to my initial quantum state. And this is that one state which I really want to learn. Right? I want to learn something about this state, right? And I can learn it by somehow detecting this thing. Well, then there is a question, how do I do that? And I do that by performing the filtering. Practically, it means that I define a temporal mode of the leaking field by convolving my instantaneous field with some filtering function, which has to be normalized such that the filtering function has to be normalized such that this temporal mode is really a proper harmonic oscillator. Basically, once this fundamental commutation relation holds, then my temporal mode is described by a proper, well-defined quantum harmonic oscillator, and I can make statements about its statistics. Right? Okay. But one thing important here is that this filtering function, I have some freedom in choosing this filtering function, right? So I want to choose such a filtering function that would maximize the contribution of whatever I want to learn about in whatever I can measure, right? And if we just, if we substitute this solution into this equation, it becomes sort of, well, it's quite easy to show that the optimal filtering function is likely this decaying exponential, right? So if I then define this proper temporal mode for my leaking light, right? I can find that my output temporal mode is not proportional to what I want to measure with such a coefficient of proportionality, which we can see that it essentially goes to 1 if I integrate it, if I measure it for sufficiently long time. Visually, we can show this. Visually, the remote looks like this. So it has a peak, let's say, in the front of the pulse, and then it decays. Okay.
So practically, how do you do it?
Practically, I do it by just measuring. In the homodyne detection, I just do it with a constant. Then practically, I'm likely sending this field to a homodyne. In the homodyne, I will have a local oscillator. I can either match the temporal profile of the local oscillator to match this temporal mode of the light, or I can just measure it fast enough. Well, here what I try to write here is that I sample this leaking field with the constant strength of the local oscillator, right? So I have many measurement reports, and then I overlay them with the weights which are set by this temporal filtering function.
Which you can do in post-processing.
Yes. Like this was done in microwaves in 2013. The first optomechanical experiment, let's say the first successful optomechanical experiment, was actually the electromechanical experiment in 2013, where they entangled pulses of microwave radiation with oscillations of a plate of a capacitor. And they did it exactly using this scheme, using exactly this method of just sampling voltages and then arranging multiple sequential samples of the voltages into this proper temporal mode. Okay, right. Okay, let me remind you that I still want to do some optomechanical entanglement, which means that now I'm not doing the readout of the cavity state. I'm trying to generate optomechanical entanglement between. Okay, I have a picture. Like, I want to send a pulse of light, which is a blue detuned pulse, so there will be two modes of interaction. I want to send it inside the cavity. I want this pulse to become entangled with the mechanical oscillator, right? And then I have to actually think carefully about which mode, which temporal mode of this heating field carries the most entanglement. Right. Okay, so like if we approach this problem very theoretically, if we assume very good parameters where the cavity mode, like intercavity mode, is adiabatically eliminated, or actually, if we are just in the regime of very good parameters, then we can rewrite all the interaction which takes place in the form which looks exactly like the two-mode squeezing interaction. And those two modes, one of them is really the mechanical oscillator, but the second mode is the optical mode, and this output optical mode has a very well-defined temporal envelope. So let's say in the essentially ideal regime of parameters, we know a very good solution for the problem of picking the good temporal mode of the leading light. The problem is that this model works for the weak coupling and assuming that there is no thermal noise, which means that in, let's say, for the levitated nanoparticles, this may not be the optimal regime of the operation. Right, and so, yeah, like this idealized solution is able to just guess this temporal mode profile from essentially writing input-output relations and trying to rewrite them in the form of the exact two-mode squeezing. And we know that in the general case, there will not be exactly the two-mode squeezing, so this sort of brings back the problem of guessing the optimal temporal profile. Right. Right, and in general, in like let's say a realistic optomechanical system, there will be quite a few parameters which influence the process of generating the entanglement from aspect relations. So we can change the coupling rate as a function of time by modulating the drive power. We can change the detuning to maybe alternate between the two-mode squeeze interaction and the beam split interaction a bit. Furthermore, we have some freedom in how do we select the output mode. So essentially, where do we look for the entanglement in the output? Right, and then we have to apply a proper figure of merit, but about this I will talk now, right? Okay, so the protocol which we consider now is the following. This is a very well-known protocol, the pump probe protocol, where we send two pulses to the cavity. The first one performs the two-mode squeezing, and when it leaves the cavity, this pulse is entangled with the mechanical oscillator. In order to verify the entanglement, well, we have to measure the mechanics somehow, and we do so by sending the second pulse. The second pulse is red detuned, and when red detuned means it's tuned on the lower mechanical sideband, it performs the state swap, right? So the first pulse is blue detuned. That's the two-mode squeezing between the light and the mechanics, and the second one swaps the state of mechanics onto the state of the pulse. So after the first pulse, we have optomechanical entanglement. After the second pulse, we now have optical Right, and when we want to verify this entanglement, actually, we have to first select the proper modes, proper temporal modes for this entanglement, and we also can choose different weaknesses for the non-classical correlation. So traditionally, when people talk about Gaussian entanglement, the very standard, necessary, and sufficient condition is having the non-negative, having a necessary and sufficient condition for Gaussian entanglement is a non-negative logarithmic negativity, which is essentially a quantity which is computed from a covariance matrix of a bipartite state. And what's important for me now is that if I want to compute logarithmic negativity, I need to know the full covariance matrix. And for a bipartite Gaussian state, such a covariance matrix has 10 independent elements, and I have to estimate each of them from doing some essentially multiple lots and lots of repetitions of my term. Okay? On the contrary, what we came with is we can search for just the minimal value, or minimal eigenvalue of this covariance matrix. It has the advantage that it is a sufficient condition for non-classical correlations. Yes, basically, if this minimal eigenvalue is less than the short noise covariance, then the state is the most weak, basically means that it has some non-classical correlation. Also, we have to verify that the two systems locally, they don't have squeezing. So basically, if the two systems that we evaluate, they don't have local squeezing, but the minimal eigenvalue of the entire covariance matrix shows squeezing, then such a system has non-classical correlations. And why practically it can be more convenient is that this minimal eigenvalue can be evaluated from just 3 elements of the covariance matrix instead of 10.
So you mean, maybe you should say the squeezing is non-local. Because why do you say, I mean, squeezing is non-classical by definition. So when you say squeezing is non-classical, it seems like tautology.
I mean, maybe, but that doesn't invalidate the statement that it's not classical.
Yeah, but you wanted to say something more.
Squeeze classical noise as well. Yes.
I mean, no.
But if you go below vacuum fluctuation, you would not call it.
But that does not say squeezing can be classical.
Yes, okay.
It's like, we're trying
But here I think you mean non-local.
I mean, yes, like we're saying non-classical correlation, right?
Yes.
Which means non-locality.
Yeah, but when you just write non-classical, it's something too general.
The squeezing is non-classical. I mean, that's a poor choice of words, probably. Maybe I could have written here that the state is non-classical. The bipartite state is non-classical because it has squeezing.
Yeah, but okay.
Which is distributed.
Because we are talking here about modes of light. So when you say non-classical, you are thinking about correlation, but already on the level of single mode state of light, we call state of light non-classical.
Yeah,
it has no entanglement. I mean, so I can have two modes which are product state, and I would still call this state of light non-classical.
Yes.
Even if there is no entanglement at all.
Right. It's not
so you should say here like they have, I don't know, some non-classical correlations or something like that.
I mean, that's what we say in paper, right? Outside of the slides.
Yeah.
Probably.
Okay.
I mean, that's exactly the point. Basically, you can have different opportunities how to get minimal eigenvalue of the covariance matrix below the short noise. One of them is to have a local squeezing.
Exactly.
This is why we have a point here that if locally there is no squeezing, then the correlation, I mean, it's like the two most squeezing is not possible. So basically, if there is the squeezing in the bipartite system, but no local squeezing, then the correlations are not possible. Yeah, this is quite easy to solve. That's well, we describes two classical states and show that they cannot have non-classical squeezing in the collective party. Right. If we do some quite simple maths, we can show that if we consider rotated quadratures in the local basis of two modes, and if we then we then combine them with the proper weights, so this gives us the so-called generalized quadrature. We can show that if each of these triangles takes the optimal value, then the variance of this quadrature essentially equals to the minimal eigenvalue of the full covariance matrix. So, well, this is really the simple algebra, and what's important is that, well, if we substitute it here, then it's clear that the variance of this quantity can be obtained from measuring only the variances of the two quadratures locally and the cross relations between them. Like here, the product has to be ordered. Whatever. The point is really that the simpler measure can be computed from only three elements of the covariance matrix. Well, if we know where to look at, right? Because we have to estimate. So we have to estimate this local rotations. We have to estimate before the experiment to set the homodyne angle appropriately. And this third angle can be found in post-processing. Right. Okay. So, yeah, then we evaluate how this class performs actually. So,
can you mention again how you measure this correlation of quadratics? So I understand that single local variables you just again do homodynes
do homodyne.
pulses.
Then we have like two pulses, and we have to measure correlations between them. I have to confess that. I don't know. But the people did that. I mean, there is a procedure to reconstruct the covariance matrix to pulses like this.
Yeah, okay, but by some homodynes. Yes.
I mean, I guess so. It has to be homodyne because they measure essential variances of quadratures. Yeah, maybe it's the debate. Okay, right. So, yeah, speaking of the performance of this sort of weakness, so here I have two axes on this plot. On the right-hand side, I have logarithmic negativity, which is the necessary and sufficient condition of entanglement. On the left-hand side, I have my generalized scheme, or this minimal eigenvalue of the covariance matrix converted to units of decibel, and we see. Right, and on the x-axis, I have the main enemy of the optomechanical experiments. This is the heating rate of the mechanical motion. All the parameters here are taken from the levitated experiment by University of Vienna, Market of the Meyer Group, where they did the ground state cooling in 2019. So they had two sort of threshold values for this. One of them is heated by collisions with residual gas in the chamber. So this quantity can be reduced by doing better evacuation of the energy. So if they go higher vacuum, this gets reduced. But eventually they reach the point where the main source of the coherence is the so-called recoil heating. This is due to the fact that the tweezer photons, they also have statistics, and they arrive in an irregular fashion. So there is some noise just because of the pattern. Okay, so, well, these are the two very important levels of noise, and well, we see that let's say, that the behavior of this remote squeezing machine designate as a matter of correlation. Repeats closing the logarithmic negativity, and there are different curves here. Like the solid line is computed assuming rotating wave approximation, and the dashed line is when I don't assume rotating wave approximation, which means that if I have the most squeeze interaction plus some residual Wimsplitter capital, the system actually performs a bit better, which seems to suggest that it's a non-trivial choice, that we only have to tune exactly on the upper mechanical side bands to try to maximize only the two most squeeze interaction. Okay, right. And this is the optical mechanical relation. So this is the entanglement at this stage. So this is a fictitious quantity because we cannot really measure it mechanically. But if we do the state swap by a second pulse and we evaluate the relations between the two optical pulses, okay, then the blue line here repeats the results of the previous graph. And between between the pulses, this is the effective squeezing. We see that it's reduced. We see that it's more sensitive to the noises, right? And okay, the solid lines assume perfect homodyne detection efficiency. Dashed lines assume attenuation of, I think, about 60%. So, like, very substantial attenuation of the light before the detection. Okay, but what's important is that still with this attenuation, the weakness of the diamond vanishes at approximately that level of noise. Okay, this is how this quantity behaves as a function of the uncertainty of the homodyne angle. So as I said before, we are trying to extract relations by trying to smartly loop in the proper locations in the current matrix, and to determine these optimal locations, we need to set the homodyne angles for the detection. And if we make a mistake and set this angle with an error, then well, there is no mistake. Obviously, we get the best results. If we tune away, then the results become worse. The different colors are what is the initial application of the mechanics. This is 10 phonons, this is 100 phonons, this is 1,000 phonons. So given the fact that now they can routinely do the initial applications of one phonon, well, then this line seems to be quite good. I want to tell you that this is like the error bars come from simulations where it is running these sample parameters with some 15% standard deviation, I think. The presence of the error bars on this plot has yielded a few citations claiming that in this paper the entanglement has been shown experimentally, which was not the case. Right. Okay, so yeah, by showing this, I wanted to convince you that if we evaluate the tunnel squeezing, so our eigenvalue, it can be done in a bit less demanding manner than doing the full Gaussian homomorphy of the state. Right, and then, like 2 more minutes probably. Like as I said before, like this system has quite a lot of numbers to define it before running the experiments, such as coupling strength, the cubing of the drive, which determines the type of interaction. Also, we need to specify which temporal mode to measure at the output, and what are the optimal homodyne angles for the detection. So we set up a simulation where we had a black box, which was like simulated not mechanical experiment, given all these parameters, and then we had the Bayesian optimization routine, which was essentially supplying sets of, well, it was supplying points in the parameter space to this experiment black box, and the black box outputted just the figure of merit. Well, the figure of merit, that was this minimal eigenvalue of the current matrix. Right? And then we got some nice results. So basically, this can be summarized that essentially as we extend the dimensionality of the parameter space, the squeezing that is generated becomes larger and larger. So if we assume exactly driving on the upper mechanical segment, so if we try to mimic exactly the two-mode squeezing, then this, like we have, in that case, we get approximately 6.7 degrees of squeezing. If we then start trying to optimize the optimal, if we start to optimize the filtering function, so if we try to look at different temporal modes at the output, it immediately gives us a tiny but an advantage. And then if we start to consider the coupling and the pulse duration as independent variables, it gives us a boost of approximately 1 dB. And if we add the tuning to that, we get 1 more dB of squeezing, probably not very reliably, but in quite a few of the cases. And, right, then, in order to simulate a realistic experiment, we also simulated what's called noisy coupling, basically to the input parameters supplied by the Bayesian optimization. When these parameters were getting some noise around the values determined by the automatic. Right? And even in presence of modes in control, it still performs better than the theoretical guess. Right. Okay, with this, come to the conclusion. Well, I hope that I convinced you that optomechanics is good for Gaussian control of mechanical motion. It can be used to generate entanglement by performing the two-mode squeezing interaction inside the mechanics. This entanglement can be read out by instant-light interaction. Then we can verify this entanglement by not doing the full tomography, but instead by doing some local partial tomography of the state. So thank you very much for the attention.
Also for speaking to time. We have time for questions.
I want to ask whether there are some practical limitations that can be given to extent regarding the possibility of using something like a factor to measure the mechanical movement, not doing a laser design.
Need to repeat the question for the sake of the
Okay.
So my question is,
I think I should repeat because I have the mic which is connected to the recording. So if there are practical limitations on measuring, on using the capacitor to measure displacement, it's difficult to answer this quickly because using the capacitor plate as a meter was what the optomechanics started from in 1970, actually. So the most obvious limitation that comes to mind is what's called standard continuity. Basically, when you read out mechanical motion, you do so by sending fields on to the mechanics. The reflected field will carry some information about the phase. In this phase, it will carry the information about the displacement of the mechanics, which you try to read out. And basically, the stronger the field that you send, the more photons you get carrying that information, the better your precision in some sense. But the more photons you send, the more you push the motion, and it causes the error when you measure it in subsequent time. And the balance between these two errors is called the standard continuity. It's just a conventional term in the theory, which can be represented by some smart things. Well, I'm not sure I can answer this question really. I hope that it's an example of it.
can you exactly say what you mean by Bayesian optimization? What do you actually do with this Bayesian optimization?
What do I mean by the Bayesian optimization? I have to confess that I did not do the Bayesian optimization. This was out what this one is who is one of the maintainers of the package of the GitHub, now had a position in the operating group. To the best of my understanding, well, Bayesian optimization is we have quite a large parameter space and it's multidimensional, and in this dimension it has quite some space. So we cannot really okay, this is the first point. The second point is that for each point in the parameter space, the evaluation of the figure of merit can be quite costly. So the role of the Bayesian optimization is that it constructs apparently its own model of the parameter space in the sense that it makes a guess on where to search, on where to evaluate the figure of merit. It makes a guess in which point of the parameter space it has to evaluate the figure of merit, and based on the result, it updates its understanding of the, let's say, parameter space. And I think what's important is that it has, let's say, in keeping its whole structure of the parameter space, Bayesian optimization also takes care of remembering the regions of the parameter space where something the figure of merit can bring the most extra knowledge. And by doing so, this procedure somehow domestically is capable of running, single value is fewer evaluations of the figure of merit than, let's say, gradient descent or other numerical techniques. But I have to confess that it's not my pair of shoes, and parroting what I heard from others.
So probably, I guess, it's important not to put no. Because if the algorithm has to go in some direction, after you know it, and you decide whether this direction is correct, and then you go back. So kind of this way it chooses the way. So I would expect it to be not with those places. But never mentioned it.
I don't know if you have one, I can search for that, but it's certainly outside of the figure. My capabilities of understanding.
Any questions for? I have one. So when you show the results of this one, could you comment on how you change the coupling? Because I understand changing the tuning is kind of easy, just you can realize it. Changing the profile, it's your post-processing.
Yeah, it's
Processing, but then the coupling is changing the potential.
Like here, like we do have some kind of, we do, okay, question, right? How do we change the coupling? We use some form of achievement because, well, if the model looks like this, if my coupling is set, well, the coupling is set by a laser power, which is described in that. So in the full model, we actually have to solve the different equations, let's say, for the circulation power, then implement the I mean, if this is a finite time, we can keep by change the power here instantaneously, then it takes some time for the intensity to break into the new value. Right here, we just for this simplicity, for the sake of simplicity, we assume that we have the magical power of changing the coupling rate, which is not, well, it's not really true for this setup where we write through the mirror, but if we use the pure spectrum setup without the mechanics, there the coupling rate also set by the parameters of the mirror. For instance, if I can rotate the polarization of the ether, I can maintain, I think I can maintain the same mechanical frequency, same starting frequency, but I can change the coupling rate almost instantaneously. Or as fast as I can rotate the polarization.
Your answer is that basically because change the power of the driving laser, but there's a problem in device.
There's lots of technical details.
It's just in here, but then it's like you actually play with the freezing.
I think so, yes. But as a disclaimer, I would say we were more on the some fundamental curiosity side, basically whether it is possible in general to get any advantage like changing this parameter instantaneously. Well, if we place, let's say, constraints on how fast we can change that, likely the result will be worse, which is normally what happens.
I want to ask a general question about the motivation. How useful is this
This is an excellent question. Well, like when people say about use, okay, the question is what can be the use of squeezed and entangled state in levitated optomechanics, right? Like when people say about useful things in optomechanics, what people normally say is that, well, the ultimate motivation for the optomechanics is either sensing or fundamental science. Well, in theory, I guess if we are capable of creating entanglement between the levitated nanoparticle and light, and the light pulse, well, we can send this light pulse to a different nanoparticle, and we can swap this entangled state to the second nanoparticle. We can create arrays of entangled nanoparticles, and ultimately this will be useful for quantum sensing. In 100 years' time, when we manage to do this at, let's say, fast repetition rate with high quality entanglement. On the other hand side, well, nobody has seen the entangled states of two massive objects so far, and therefore it will can be useful for the fundamental science in this sense. Well, it's all pretty abstract, right? That's the best that I can